We're going to be working to graph linear equations in this section, as well as understand the different characteristics of the graphs of lines. So it is true that whenever we're dealing with lines, we can always represent lines with an equation, and if that equation defines a line, we call it a linear equation. Now, most of the time, lines are going to be functions, like when you have a positive slope line or a negative slope line, so really any diagonal line, as well as when you have a horizontal line. All of those are functions because each input maps to exactly one output. They all pass the vertical line test. The one case where you don't have a function is when you have a vertical line, so a line that has an undefined slope. Because there it doesn't pass the vertical line test, you have an input that's going to multiple different outputs. So most of the time you're able to have a linear function, and when you do so, you can always write the linear equation of the form y equals some number times x plus some other number, which you're probably familiar with as being like y equals m, which is the slope, times x plus b, which is the y-intercept of the line. So as we work our way through lines, and not only lines, is going to be really critical for us to understand solutions when we get to graphs that aren't lines in the future as well. So a solution is really just something that's going to make your equation or inequality or whatever it might be true. So if you have like the relationship like 3x minus 5 is greater than 16, it turns out that like x equals 8 is a solution. There's actually a lot of solutions right here, and that's true because if you substituted 8 in for x, you end up getting 19 on the left-hand side, and of course 19 is greater than 16. Now, you also can have it so that you have like ordered pairs that might be solutions to things at times. So if you have like an equation where like negative 2x plus 5y is going to be equal to, say, like 16, then it turns out that the ordered pair negative 3, 2 is a solution to that, because if you did put in negative 3 there and 2 right there, you do end up getting a sum that's exactly equal to 16. So that's what it kind of means to be a solution, and that's really important because if it's a solution to an equation or inequality, it's going to be a point that's reflected in the graph of that particular relation. So we're going to see that if graphs kind of all have the same shape as one another, so in that case those are all lines, or those graphs kind of all have the same shape as one another, or those graphs all have the same shape as one another, then we would say that they belong to the same function family as one another, and the equations that define graphs that have the same shape will all be similar in nature to one another. So I just want to introduce that terminology to us. Right now we're only focusing on lines for now, and we'll get into territories of other graphs later on. So a function family is really going to be a family of functions whose graphs are all the same. Now, in each function family, there's going to be what we call the parent function, which is kind of like the most plain, basic sort of function we can define for that family. So for the linear family, or for the line family, it turns out that this line right here, this diagonal line that has a positive slope of 1 passing through the origin, is going to be the parent function for lines. It actually has the equation where all of the y values are equal to the x values, and you can see that is definitely true because you have like 6, 6 right there, or down here you have negative 7.5, negative 7.5, or 0, 0, right? All of the x values and the y values are the same. So that is the parent linear function that we have for lines. So in general, most of the time we are able to write lines in what we call slope-intercept form. And it's called slope-intercept form for a reason, because when we have it of the form y equals mx plus b, where the slope is m, and then it has a y-intercept of b, then the equation tells you explicitly what the slope is, as well as what the y-intercept of the line is. So it's really important that you understand that when we're finding intercepts of lines, you can see that an intercept is going to be where it crosses an axis. And so here, where it crosses the x-axis would be denoted as the x-intercept. But it's a point where it crosses. You can't say the x-intercept is 4. The x-intercept of that line is actually the ordered pair 4, 0. So make sure you always specify an intercept as really being an ordered pair. And then similarly for the y-intercept right there, that's going to be the ordered pair 0, negative 2. So those will give us intercepts. So I want to show us where slope-intercept form is ultimately going to come from. And so I'm going to pick some points on this line. And I'm actually going to pick this point right here, which would have a 0 for an x-coordinate. And then we don't really know necessarily how high on the y-axis it is. So let's just assume that it's going to be some number b. So that point actually really is truly like the y-intercept, right? And then I'll just choose any other arbitrary point that has some x-coordinate and then some y-coordinate, of course. So one thing that we do know is true about lines is that we can find the slope of a line, and the slope of the line would be finding the change in the y's. So it would be taking y minus b and then dividing that by the change in the x's to find the run, and that there would be the run, which would be taking x minus 0. And so based on this relationship of slope right here, really it just simplifies down to m equals y minus b over just x, because x minus 0 is just x. And so I'm just going to manipulate that equation a little bit. I'm going to do something to both sides right here. I'm going to times both sides by x. And what you're going to get out of that then is m times x is going to equal y minus b. And then from there, by adding b to both sides of that equation there, you're going to end up with the fact that mx plus b is equal to y. And so you can see that's exactly where slope-intercept form is coming from. It's just coming from the slope of a line, where you can see that there's the slope timesing with x, and then b right there is the actual y-coordinate where the y-intercept is occurring at in particular. So this is really helpful for us in graphing linear equations when you've got your equation in a form where you do have y equals mx plus b, and it's in that particular form. So when you write an equation in y equals mx plus b form, it should be very explicit and apparent that the number that times with x is going to be the slope of your line. So in this case, the slope of this line is 4. And then also, because we're adding -5, that's going to be where the y-intercept is. So the y-intercept, you always want to specify it with ordered pairs, is going to be 0, -5. So then to be able to graph this line then you should just be able to plot the point where the y-intercept is at, which would be at 0, -5. And then because it has a slope of 4, you can treat that as being 4 over 1, which then tells you that if you go at a rise of 4 and a run of 1, then you can find more ordered pairs that are going to be on this line, y equals 4x minus 5. And then, of course, you can connect those dots and draw some arrows to be able to sketch out that line. Now, to be able to find the x-intercept, you can see that the x-intercept right there is going to be a decimal. And so what we know to be true about any x-intercept, so no matter where it crosses through on the x-axis, is the fact that its y-coordinate is always going to be 0, right? We don't know necessarily the x-coordinate, so hence the question mark right there, but we know the y-coordinate is 0. And so if a point is going to be on a line, it should satisfy that linear equation, meaning that if I plug in the x into the equation and I plug in the y into the equation, it should make that number statement true. So that means to be able to find an x-intercept, you can substitute 0 in for y and then actually solve for the x. So if I substitute that 0 in for the y, I get this equation, and then just add 5 to both sides and divide by 4, and it turns out that you get 5/4 is equal to x. So 5/4, which is 1.25 as a decimal, would actually be the x-intercept of that particular line. And then right next door right here, you'll notice that it says y equals 7 minus x. Now you can treat that as being -x plus 7 if you want to write it in that form. And that should tell you then that because y is solved for alone, this is in mx plus b form. So that should tell you that the number that times with x, which is going to be -1, is going to be the slope of your line. And then plus 7 is going to tell you the y-intercept. So it's going to cross through the point 0, 7. So to graph this, you start at your y-intercept. So plot that point first, and that's going to be where 0, 7 is located. And then because it has a -1 slope, you can treat that as a rise of -1 and a run of 1. So it should go down 1 and over 1. So just like this is going to be what the line is going to go like right there. It does turn out that you have a nice x-intercept because it ended up hitting this dot right here at 7 nicely. But we could also find the x-intercept knowing that any x-intercept is going to have a 0 for the y-coordinate. So if you did substitute 0 in for y into the equation, 0 equals 7 minus x. Then if you subtracted 7, -7 would equal -x, and then divide by -1, you get a positive 7 for x, which then means that, oh, hey, yeah, the x-intercept is indeed at positive 7 right there.